everyone, I'm Stephanie Peer, and welcome to the Salt-Tea Podcast, and welcome to a special segment I like to call Chemical Corner, where we get up close and personal with some of the great chemistry that's happening all over the world in our oceans. And in this first Chemical Corner episode, we're going to start out by taking a quick look at how we classify some of the major elements and compounds found in seawater. Okay, so to start this episode, let's quickly refresh our memories on a few chemistry concepts. If you've ever taken a chemistry class, you may remember seeing a large poster with brightly colored boxes with capital letters and lowercase letters written in each box along with some numbers. And as you'll recall, we call this series of boxes with letters and numbers the periodic table. And the periodic table is just a way that we visually organize all of the different elements that we've discovered or created on planet Earth. Elements such as oxygen, carbon, nitrogen, and the ocean is full of all the different types of elements, whether they're dissolved in the seawater, such as the ions that make our ocean salty, or as solid particles floating within the water column or sinking to the bottom, or even as gas and bubbles. And an atom of an element can combine with other atoms to form what we call molecules, and these molecules can be made up of only one type of element, such as oxygen and another oxygen atom, making up what we call an oxygen molecule. Or molecules can be different combinations of different types of atoms, such as carbon dioxide, which is two oxygen atoms combined with one carbon atom. Or we even have nitrate, which is one nitrogen atom combined with three oxygen atoms. And you'll remember from episode 1 and 2 that if molecules or single atoms have an electrical charge to them, we call them ions. Okay, so that's enough of a review for now, so let's dive into this week's episode. Alright, so to start us out, let's look at a few terms and definitions. So when I say the word concentration, I mean basically how much, or how much of something. And in marine science, we often reference a concentration to a specific volume of water. So for example, when we talk about salinity, we're talking about the concentration of salt, or the amount of salt, in a specific volume of water. And in science, we use the metric system. So we're going to say the concentration of salt in grams in a volume of water, which would be a liter. And concentrations of different elements and compounds found in our ocean depends on the different inputs or sources adding them to the water, as well as the different sinks or what's taking them out of the water. And sources and sinks can be due to different processes. So they can be due to physical processes such as water moving and mixing, or they can be biological, such as plants producing oxygen through photosynthesis, or fish and little critters removing oxygen when they breathe. Okay, so the next term I want to introduce you to is residence time. So when I say residence time, I mean how long or how much time something has stayed in a particular area or body of water. And again, residence time can be due to physical processes such as how long it takes water to move in and out of an estuary, or how long it takes a particle to ride the global ocean conveyor belt. Or it can even be due to something biological, like how long does it take an oyster and a fish to eat a phytoplankton in the water. So it can mean different things, but it ultimately is referring to an amount of time that something is spending in a particular area or volume of water. And finally, I want to give you two new definitions for the words dissolved and particle. So when I say the word dissolved, here at Salt-Tea Science, I am referring to an element or a molecule or something that is super small, and specifically smaller than 0.45 micrometers. And then when I say the word particle, here at Salt-Tea Science, I am referring to something that is larger than 0.45 micrometers. And just to give you a reference, the diameter of one strand of hair is about 20 to 40 micrometers, and maybe even 100 micrometers if you have really thick hair. And then even smaller, the diameter of one piece of spiderweb silk is about 2 to 3 micrometers. And then the size of bacteria are about 1 micrometer. So when I say that something is dissolved, it means that it's less than 0.5 micrometers, which means it's really small, smaller than bacteria, which then also means that it can usually stay suspended in the water. And then, of course, when I say something is a particle, or say that something is in a particulate form, I'm then just referring to something that is larger than 0.45 micrometers, or larger than, say, a really small bacteria. Alright, so now let's turn our attention to the elements and compounds found in seawater. So you might have noticed by now that scientists like to simplify our very complex world by putting things into different categories or classifications. And in marine science, we like to do the exact same thing. And so we even like to categorize the different elements and compounds found in seawater. And so we'll classify things by different characteristics of the property. So for example, we'll classify by size, like I just said, by saying something's dissolved or particulate. But then we'll also classify things by saying something is organic or inorganic. And finally, we'll classify things by saying whether they're conservative or non-conservative. And if we say it's non-conservative, we then further subdivide it into saying whether it's a nutrient type or a scavenge type. Okay, so what do we mean by conservative versus non-conservative? And no, I don't mean that the elements in seawater belong to different political parties. So when we say that an element is conservative, we mean that it occurs or is found in a constant proportion throughout the water column. And if there are proportion changes, they generally occur very slowly through time. On the other hand, when we say something is non-conservative, it means that the quantity or proportion is generally connected to biological or seasonal cycles. Alright, so now let's take a slightly closer look at conservative elements. So when it comes to seawater, most of our conservative type elements are the major ions that make up all the salts in our seawater, such as sodium, chloride, magnesium, and potassium, just to name a few. And we call them conservative because they're mostly unreactive and bio-unlimited. For example, calcium is an element that many different organisms need to grow and make seashells, but there's so much calcium in the ocean that these organisms will never, ever, ever, for the most part, run out of calcium. And when it comes to conservative elements, they generally come in fixed proportions throughout the water column, and their quantity or concentration is mainly controlled by physical processes such as evaporation or precipitation, or even dilution due to rivers and freshwater runoffs. And so conservative elements are also known to have very long residence times. And these residence times can be so long, they can be even up to 1,000 years or longer, which also means they've gone through the global ocean conveyor belt multiple times. And one of the great things to know about knowing which elements are conservative is that we can use this knowledge to help us understand what's going on in the water, as well as establish constants or norms. For example, we are able to calculate and understand salinity because of the conservative nature of the ions that make up the sea salts in our seawater. And so this helps us establish what is quote-unquote normal, which then knowing this helps us to also identify non-conservative elements. Which now brings me to non-conservative elements. So non-conservative elements are generally the trace gases and nutrients and trace metals and dissolved organic compounds which have much shorter residence times, from thousands of years down to years, maybe months, days, hours, and even possibly seconds, depending on what and where they are. And they could be controlled by physical processes such as water movement and currents and tides, or they more likely are controlled by biological processes such as photosynthesis and respiration. And so when it comes to non-conservative element types, we can then further subdivide them as either nutrient type or scavenge type. And nutrient types are stuff like your macronutrients like nitrogen and phosphorus, as well as your micronutrients such as zinc and copper and iron. And they're the elements that plants and animals need in order to grow and survive, which also means that their concentrations are dominated by what we call biological uptake and recycling. And because of these biological demands and processes, we can see general trends of concentrations within the water column. So for example, the elements that plants need to grow, like nitrogen and phosphorus, we generally see that the surface waters have very low concentrations. Why? Because the plants are using them. They're sucking them up like a juicy burrito. But then the deeper we go, we start seeing rapid increases in concentrations until a point which generally we call the mid-depth maximum, in a region we refer to as the ONZ, or oxygen minimum zone. But don't worry, more on that in another episode. And this maxima, or this high concentration of these elements, is due to a biological process called respiration. And respiration occurs by all sorts of different marine organisms, from microscopic bacteria all the way up to fish and even whales. And then below that maximum concentration, or that mid-depth maxima, we start to see about the same concentration the deeper we go, which this is generally due to water moving and mixing. And then, of course, our last type of non-conservative elements are the scavenge-type elements. And these include aluminum, lead, manganese, and gallium, just to name a few. And these elements tend to have very short residence times in the water column because they tend to be sticky and they like to stick or adsorb to other particles, making them quickly sink to the bottom of the ocean. And scavenge-type elements also show general trends in the ocean. We generally see higher concentrations at the surface and then lower and lower concentrations the deeper we go. Unless, of course, there is a deep water source, like our hydrothermal vents, which then we would see higher concentrations near its sources. And so in comparing conservative versus nutrient type and scavenge type, if we had the technology from the TV show The Magic School Bus, we'd hop into a school bus that transforms into a submarine that would then shrink down to the size of the dissolved elements in the ocean, and we'd see how the concentration of conservative nutrient type and scavenge type elements change with depth. And then of course we'd see that conservative element concentrations for the most part stay the same, regardless if you're at the surface all the way down to the bottom. While nutrient types go from very low concentrations at the surface to higher concentrations the deeper we go. But scavenge type elements are the opposite, where we have high concentrations at the surface and low concentrations at the bottom. And so because we know what the general trends should look like for conservative versus non-conservative elements, if we take water samples and see that concentrations are not quote-unquote normal, we know that something must be happening, and now we can start an investigation. Alright, so now it's time for our 1-minute summary. In this episode, we started looking at how we categorize the major elements found in seawater. We said that the elements can be thought of as either conservative or non-conservative. All conservative elements, for the most part, have really long residence times and are generally found in fixed proportions, like the major ions in seawater that make our water salty, and their concentrations are generally controlled by physical processes such as dilution, evaporation, and precipitation. Then we said non-conservative elements are generally the trace gases, nutrients, trace metals, and dissolved organic compounds, which have much shorter residence times and are controlled by physical and biological processes. And then non-conservative elements can be further subdivided as your nutrient types, like your macro micronutrients, which are required by plants and animals to grow and live, and of course as your scavenge type, which are your very sticky and also very reactive elements, so they have a very short water column residence time and are generally found sinking to the bottom of the ocean. And of course, finally, knowing about different types of categories and concentrations of the different elements helps us determine and understand what is happening in our oceans. And that's the end of our 1-minute summary. Alright, so before I say goodbye, I'll remind you to check out the Salty Science Weebly page to find great images, videos, and links that correspond to each episode. And if you're a Salty Science crew member, don't forget to go to the Salty Science Patreon page, because I'm posting pictures of the development of my salt crystal experiment, which have now had 2 weeks to go, and they've started to get really big. So we have to start deciding how we want to turn them into our winter decorations. And listeners, if you're not a Salty Science crew member yet, you can join our crew by going to the Salty Science Patreon page today. And with that said, I'll remind us to all do at least one thing this week to help keep our beautiful oceans and our waterways clean. And then, of course, don't forget to always stay salty. Thank you for listening to Salty Science. But guess what? You don't have to let the fun end here. Go to www.saltysciencepodcast.weebly.com, where I've posted some cool videos, my study notes, and some really neat experiments that you can try at home. And if you want to follow along with my own research, you can follow me on Instagram. User handle Teps Adventure. That's TEPS Adventure. All Salty Science episodes are available on iTunes, Spotify, Google Podcast, and YouTube, plus a number of other podcasting apps. If you like the show, please rate, review, and subscribe on iTunes, as this is the best way to spread the word about this podcast. Salty Science is listener supported, so if you would like to show your support, visit our Patreon page at www.patreon.com/Salty Science, where you can either make a one-time donation of any amount or join the Salty Science crew for as little as $1 a month. So visit the Salty Science Patreon and sign up today.